Okay, so let's welcome our next speaker, who's Jenny Leclaire from the University of Mainz. And she will tell us about the structure-based bioinformatics with BiochemicalAlgorithms.jl.
Thank you for the introduction. Now? Yes. Now it's louder, sorry. Then I will start again. But does it work? Yeah. Sorry. So, thanks again for the introduction. And my name is Jenny Leclaire, now with microphone turned on. Classics. I'm a PhD student at the Scientific Computing and Bioinformatics group in Mainz. It's the first time for me at the JuliaCon, so I'm really excited about the whole event, and I hope you can enjoy also the JuliaCon and especially my talk today. Um, it will be structure-based bioinformatics with biochemical algorithms. First, I will give you a short introduction into structure-based bioinformatics. Then I'm going to talk a little bit about the biochemical algorithms library, or short BAL. I will just call it BAL because it's very long. We will dive back into the 90s and see the design goals back then. Then we will look at our new package, BiochemicalAlgorithms.jl, how we designed that one, and look at the core structures and the performance on some typical tasks. And then I want to show you some applications, so initial things we can do already, and what we are currently working on, and how this all fits into the Julia universe. So I would say we directly get started. Structure-based bioinformatics. What is structure-based bioinformatics? It's a research field working with three-dimensional structures of proteins or combinations of proteins and nucleic acids. And I wrote now the revival of a research field because for some time ago it was getting a little bit quiet in this area because people were turning into proteomics directions, and the main reason why it got fancy again, or modern again, is due to 3 points in my perspective. So the first one is related to data. As you can see, I put here the plot of the number of released PDB structures per year, and for each different experimental structures. So the PDB is the most important protein data structure data bank. And there were some advances in the electron microscopy area, so that we have more data structures available. But there is also advances in algorithmics that lead to the fact that we have more data we can work on. And this is due to AlphaFold. So both together we have more data available which we can work on. And the other reason why we are really interested in data structures, because I don't know what you did, but a lot of people started in 2020 to sit in their home offices and trying to dock some corona proteins and find a track for that. So first, what is software development in structure-based bioinformatics? It's really a highly non-trivial task, because the things we want to implement, they really need performance, such as structure minimization, molecular docking, or molecular dynamic simulations. And the development of these applications are really, really challenging. So why? Most of the packages were at the high phase of structure-based bioinformatics in 90s, starting from the 90s to 2010, and they are still used up to date because we don't have any more new tools. The performance, as I said, is already required, and the development times shouldn't be that high. It should be actually easy to develop these tools because we need them. And it's dependent on the programming language you choose. Most of the software packages we have in this area focus on one specific task. For example, the implementation of a force field, or the preparation of the molecule, or just for a simulation package. Biochemical algorithms, which are short is for BAL, it focuses on the entire pipeline you can have in a scenario. So it includes basic stuff you can use just to get started. But if you want to use your own force field implementation, the interface is structured so that you can do that. It also comes with a visualization tool, which is called Ball View, that leads you directly gives you an idea how your docking scenario looks like. So I will have to talk a little bit about Ball and C++ code first, because that's how it influences our new design of it. So, but there will also be the biochemical visualization package, which we started to implement. But today we only focus on the left part, so to say. Okay, so Ball, what is Ball? The work on Ball started in 1996. It was majorly published in 2000, and in 2010 there was a major release where they added some good new advances, for example, the Python interface, and they switched to the C++ build system. Ball itself has used to have a very large user community, because it is one-of-a-kind package. Even pharmaceutical companies were using Ball software. And this is because it had tools for the entire pipeline. And it's open source, of course. So how is it structured? So you have the standard library, it's a layer structure, and at the bottom you have the standard library, then you have the foundation classes, because if you want to provide software working on different operating systems and on different operating compilers, then you have to adapt your code according to it. And therefore we have some foundation classes that also give data structures for strings and for necessary things like the hash trees and so on. Then we have the kernel, that is basically the core piece of the software. And then we have all the functionalities on top, like a visualization and molecular mechanics pieces. Then on top of that, there resides the actual application that comprises, there are predefined tools you can directly use, or you can try to write your own tools. And on top there's the Python interface that was available since 2010. And of course here on the left you see the necessary packages for the visualization. So this was our C++ library for many years, and it's still, you can still use it, you can download it, you can work with it. That's the kernel. So this is the heart of the software. It's really nicely grafted, by the way. So you use the composite pattern, and every molecular entity, if you want to model that, it's a hierarchical pattern, because you have a molecule, the molecule consists of chains, the chains can have residues, and so on. And this is implemented via the composite pattern. So why I'm only talking now about design goals, a little late after but it's important for the new design. So previously the design goals were ease of use, functionality, openness, and robustness. Ease of use, back then there was the decision to use C++, and it was the optimal choice to implement the software, because we didn't have Julia back then. They wrote an intuitive interface. They provided a lot of functionalities, as we already saw. It is open. You can interchange parts that you want to write on your own, and it is a highly robust library that was part of the success of Ball, because the code is really intensively documented, tested, and corrected for code. But let's look at it from a 2024 perspective. Basically, this is a classic language problem we are facing. So they use C++, and by far it's really performant, but it's not anymore used in the user group. The CMake build system made it easier, but it's still not a trivial task to work with it or to develop your applications. And especially dependency hell if you want to include new libraries. The functionality is still highly required. We need that. There are not so many other options to have this. So that leads us to the introduction of BiochemicalAlgorithms.jl, our new redesign. And it has similar design goals because we have ease of use, but for us, really important was rapid application development. So the user should be able to directly write down their ideas for a code. And of course, if you're dealing with molecular mechanics, you need efficiency. So why again Julia? It's Julia. Obviously, we all know Julia, we want Julia, it's fine, but just 3 reasons why it's nice to have it for this design. Performance is clear. It solves the 2 language problem, I already said that. And less boilerplate code. So the domain expert should be able to write their ideas down fastly, and it is highly readable. The package manager makes things much more easy together with the Julia universe. So there are really good packages for specific purposes that we can use already. And one thing that always defines the quality of a scientific package, the availability of documentation, testing, and benchmarking, which can be integrated in a very straightforward manner in our case. So that's where the main reasons to choose Julia. This is a UML diagram for our system. Don't worry if you cannot read all the attributes. The important point here is that our system is at the center. And from this, all other molecular entities, such as residues, chains, and atoms and bonds, are part of it. So I think it's time for a little bit of water, right? Half time. Let's generate some water. So it's just to give you an idea that all the boilerplate is now gone compared to C++ code. We can create our system here. Then we have our molecule. We just create some atoms, set the position of the atoms, create a bond, and basically also can visualize these things. And it looks like our Mickey Mouse that we are always using. It is really straightforward to use. So now a little bit try again. How can we represent atoms and bonds? Because they are the key parts of every simulation, right? Atoms and bonds. That needs to be fast. So the first idea which we had were, of course, data frames. And we implemented that, and it was fairly fine to use. The advantages were very intuitive usage, but for our scenarios, it was just not performant enough. So what we did else then look at was atom space. Atom space is a package from the Julia Molecular Simulation Group, and we were looking at that, and it just doesn't provide all the necessary functionalities we needed. So what we are planning is to be compatible to atom space, which is straightforward. And what we did then is that we used the table.jl interface, which data frames is actually based on. So we implemented our own kernel for that, based on tables.jl, which has the advantage that we directly can convert it to data frames. Sorry, unfortunately the slide is cut, but just to give you some preliminary performance results. If you just plainly write down your code in Julia, it works fine, it works, but it gets, you always have to tweak a little bit of performance reasons. Yeah, and we did that for the Amber 4 suite, we already did that, and for some performance functionalities of the core, we still have to do it. Okay? But it works in general. Sometimes we are faster, sometimes the C++ code is still faster, but yeah, that's the main take-home message. Applications, let's look at some code again. One thing you always do when you, for example, work with conformations of proteins is that you want to compare protein structures that are similar, that have the same amino acid sequence or something like that. And you can already do that with BiochemicalAlgorithms.jl. You just read in your data, and then you apply the fragment database, which is shown here in line 3. This is really one advantage of our package, that you can it provides the code to prepare the molecule, because in the data formats, not all the necessary information is included. Sometimes data is missing. Then you can reconstruct it, the fragments. The bonds are not contained, that's why we have to create bonds. But if you just plainly read the file, then you get a number of atoms here that are, of course, still not connected. Once you reconstruct the bonds, so that's basically what the fragment database can do, then you see the connections, the bonds, you have that. Then you can, of course, compute the RMSD for the two structures. Before we map the structures, it's 5.4. After mapping, it's 1.4. Another application, if you're now interested, okay, how is the energy of the two systems? Are they comparable? Where are differences? Then you can just apply the amber force field. And if you do that with the verbose information, then you get each of the components, and you can take that and compare it to the other protein structure. So what is out now? What is the next move? What do we want to do? Currently, as I said, we are still looking at the performance to tweak a little bit of performance yet. We want to do scaling benchmarking. So how does it work with bigger inputs? Is it still very good, or what do we have to do to keep the performance? Then we are looking at the PDB reader at the moment, because we need the support from some information that is contained in the PDB reader, such as alternative location IDs. That is still really important. Then we wanted to implement another force field, the charm force field. And then we are looking forward to our package registration that we just started and the official release. And then we head forward to molecular docking and continue to work on the biochemical visualization part. So how does that all fall into the Julia universe? I just saw Joe, you're also here. He's actually you have also a talk, and he's the writer of the MolyJL package, the molecular dynamics package, and I think we can really work together there. We have definitely connections there. And then there's the Protosyn package that mainly focuses on peptides and modification of peptides and sequence structures. And then there are two big communities, the BioJulia communities we are already using, and the molecular simulation in Julia, where atom space is coming from. So I think definitely we can work together. If you have now ideas, please talk to us. We are here until Friday if you want to contribute, or if we can do something for you, just let us know. We are happy to have more input. And with that, I would like to summarize quickly. So the BiochemicalAlgorithms.jl is a redesign of the popular BALL framework. It attempts to cover the entire molecular modeling pipeline. It is not yet feature complete towards the C++ predecessor, but we are working on that. But it allows for rapid prototyping of ideas, and the design is so flexible that you can implement your own ideas in this interface. Acknowledgements. I would like to thank Professor Hildebrand and Thomas Kemmer. We are actually the core team behind BiochemicalAlgorithms.jl. And then we have other contributors and the rest of our group that are working on it. And I would like to thank you for your attention. And I'm happy to ask questions if you have any. Thank you.
Yeah, thanks, Jenny. We have plenty of time for questions. So.
Great talk, thanks a lot.
Thanks.
One of the cool uses for this would be kind of setting up simulations which would involve reading force field files, topology files in kind of 1,000 different incompatible formats. So is there any plans for that, or maybe using chem files or something?
Yes, definitely. We are planning to work on that. So the previous BALL library also included that, and we are actually working on it.
Hello, nice work. We are currently preparing a project applications for repurposing proteins of bacteria for food applications. So, for example, whether they're suitable for emulsions or making foam and so on. Could we use your package for that, and what could we do for that? These are all properties that are based on structure, like if they can bind water and how much, or if they can access lipids and so on. And these are things based on the 3D structure, but could we use this suite of algorithms for that?
It depends what you're actually looking at concretely. But in general, yes, of course, you can load your structures there in the PDB format, and also we support 2 other formats. And then you can read it, you can visualize it, and you can make comparisons of that. Or maybe, yeah.
Just quickly answer that.
Maybe we have a microphone? Sorry.
Thank you. So where it can probably mostly help you with is getting the whole things connected. So the idea of BAL was never to be the one place that had the world's best, say, molecular dynamic simulation or the world's best docking tool. You have MD code there, you have docking code there, but there are specialized players in that who do that much better. They have much more effort put into it. But you typically cannot just download such a tool and just use it. There's a lot of preparatory work. There's a lot of work going in connecting these things. And that is non-trivial work. So for instance, like when Jenny showed, when you download the structures and all the bonds are missing and so on, you have to recognize what kind of chemical structure that was and to add the correct bonds to the correct locations, figure out what the atom types are. All these kinds of things there, it can help tremendously. So it would probably particularly help you in gluing other stuff together or writing your own code. If you want to work with these kinds of things, if you want to compute forces, if you want to minimize molecules, or if you want to write a docking program or run a docking program or analyze the results of a docking program, all these kinds of things are much easier using this kind of code than doing it from scratch.
Other questions? Or ideas? Yes?
Is there any electrostatics work inside of that?
Yes, yes, we have actually, the expert is sitting there. It's Dr. Kemmer actually wrote his thesis about electrostatics. It's called the Nessie JL paper.
It started as a way to compute non-local electrostatics because that wasn't really fun to do in C++. And so the standard electrostatics stuff is, of course, there the Coulomb stuff and so on, but we also have BEM and FEM code for solvate electrostatics.
Wow.
Do you have a I'm sorry? Can you pass?
So do you have a particle mesh UOLD?
Sorry, what?
Not sure if I understood it.
UOLD summation, so particle mesh UOLD.
Oh, I see. No, not yet. Not yet. Sorry, we don't have PME yet, but it's on our list.
Yeah. So you mentioned minimization of structures. Is that also something that it does?
Yes.
Yeah.
Yes.
So basically all of the things that we can think about.
Yes. Maybe they are not all yet implemented, but we are working on it.
Structural alignment, so aligning structures.
Not yet. I think that
But you're
in the C++ code
Yeah.
not yet ported.
okay.
yes.
To Julia.
Sometimes we are surprised what Ball offered, to be honest, because it was there for such a long time, and whole generations of PhD students and students worked on it and developed applications because the framework was so open that sometimes even we are thinking, oh yes, there was something.
Okay, if I may ask, how is your experience in migrating such a large code base from C++ to Julia?
Yeah, I mean, once you fight through all the boilerplate, we are just at the beginning, but it feels so naturally to write the code down in Julia compared to C++. It's I mean, we are also. I just gave an experience talk on teaching, because we are using our software for 2 years also as a teaching, and the students only know 1 year of programming experience. They are diverse. They have a diverse background. They are computer scientists, physicists, mathematics, and of course biologists. And they started to work with the software, and they were really, really happy and relieved to switch from C++ to Julia, and to work with BiochemicalAlgorithms.jl. So just to have everything together and not being overly frustrated about boiler code in C++.
Yeah, that's nice to hear. Anything you miss from the C++ world?
I mean, it's always nice to have to just get starting and to write down your ideas in Julia, but all the frustration you learned through C++ and setting up software in different platforms, you can learn a lot there, I would say. That is that keeps you busy. It keeps you busy nights and days, and increases your frustration tolerance, but not necessarily helps you in getting the task done you're actually interested in.
Maybe I can add
Yeah.
2 things so maybe just 2 things. One is that, I mean, while Julia gives great performance, the C++ code was pretty performant, but it was optimized over many, many years.
Yes.
And it turns out, as you probably all know, if you want to have really high performant, non-trivial Julia code, you have to do things, and those things are not often straightforward to understand. So you have to learn a different way about thinking of how to make your code faster.
Yeah.
And I mean, that's not necessarily a disadvantage. It's just something that is completely different than it was. And most people who are new, in our case, are new to it, don't understand it yet. The second thing, the only real thing that is maybe, I don't know, maybe just a little bit scary. I mean, there's so much great stuff in Julia, so many great packages. What is often a little bit unclear is if we can rely on them for a longer time. Because, of course, much of it is done in academia, is done through PhD students and postdocs and so on. And we intend to support this for a very long time, like we did the last thing. And we don't want to reinvent the wheel all the time. So we want to use all these exciting packages in Julia. But there it's, that's something that we have to figure out, where we can rely on it or where we need to have a backup plan or whatever.
Mm-hmm.
I mean, one possibility would be to help maintaining then.
That's, I mean, for things that are really important, that's probably what's going to happen, yeah.
Great. So thank you for your talk. It was
you.
really interesting. So one round of applause